So I wanted to introduce tonight's speaker, Mr. David McColl. And Mr. McColl is one of these people that has about as many degrees as I have fingers. And let's see if I can get this right. So David has a bachelor's degree in engineering physics from Queen's University. Yeah. He has a master's degree in nuclear engineering from a kind of a smallest school that I really haven't heard of, UC Berkeley. He also has an MBA, I believe, is that right? And also a master's in education. So he knows what he's talking about. If you've been to the tutoring center any time during the last 5 or 6 years and done anything in chemistry or physics or engineering, it's possible that you've worked with David. So we're very pleased to have David here tonight. He's going to give a lecture on what physicists understand to be the so-called standard model of physics. And as you'll hear, he's going to kind of center his talk around tonight around literally what's inside of a proton. So please welcome David McColl.
Thank you, Don. And I'm going to put on my professor cap, and we have a question on the board here. So who knows the answer to the question? Can you just put up your hands? How many people know what's inside of a proton? Go on, don't be bashful. Yeah, you got some ideas what's inside of a proton? Yeah, I know, you do. Not a lot of people know this. I was going to ask if a bunch of people, because a lot of people read about this in science magazines and things like that, but it doesn't seem to ever really get taught in school. So I sort of thought that was sort of a bit of a hole in what we convey to all of our students about what the world is made of. I'm going to start off with just a little bit of review about how science works. This is really a story of how we figured out what we think the smallest bits of our world are made of. So we had to we're going to do a little review on how science works. And we're just going to use, the planets in the skies and remember how that happens. Then we're going to look at 3 different forces. The first one is the electromagnetic force. And that's how we make atoms. We're going to make atoms with electrons and everything. And mostly people have done this in chemistry. We're going to go a little bit farther, so hold on to your hats for that one. Then after that, we're going to talk about the strong force. This is what holds the nucleus together. So everyone knows that there's protons and they're all there in the nucleus. Well, if I have 2 plus charges, do they attract or repel? They repel. So how come the nucleus just doesn't fly apart? That's part of the story we're going to tell, and that's about the strong force. And then, but does every atom stay together all the time? Sometimes you get radioactivity and things fall apart. That's going to be our 3rd force that we talk about, and that's called the weak nuclear force. It actually does a lot of stuff. It's weak because it doesn't happen very often or very fast. And then we're just going to put it all together. Once we have all of the bits and pieces, all the players that have been doing this, we're going to put this together. It's called the standard model of the physics of what we're made of, what everyone here is made up of, what the stars in the skies are made up of, and everything. So let's move right along. We're going to start off with motion in the heavens. And so one of the first things that happened, Tycho Brahe, he had a telescope, and he was looking there, and he was measuring where all his planets were. And Johannes Kepler comes along, he takes those measurements and says, if I do that, I can say, and what kind of orbits did they make? Anyone remember? Pardon? Elliptical, that's right. And that was actually a big deal in those days, because they said, no, it had to be circles, but no, it's elliptical. And then this fellow Newton comes along. He's got his 3 laws, and he makes some calculus stuff, and he puts together and says, hey, I can explain these orbits with this 1/r² law of gravity. And in the meantime, other people are still looking up in the skies. This guy, Herschel, he discovers Uranus just by chance. He's sort of looking up there, notice that this kept moving every night, so he'd look at that. And then, so when we think about science, these 2 things here, that's evidence. Those are observations that we made. Kepler, he made a model of what was going on. It was sort of a qualitative model is, yeah, they go in ellipses and they do these sorts of things. But Newton went a little bit farther. He developed some tools and some technology, and he put together this quantitative theory. This is a theory that could predict where things would be, and in a typical move, they make predictions. If I see something, if this thing here is happening, then that thing there should be going on. And one of the things that they did with this is someone was looking at this orbit of Uranus here and said, there's something funny with this orbit. It's not quite where it should be. If this thing is doing what it's doing, there's got to be something else out there. So they predicted where another planet would be. They went and looked there, and they found it. This is how a really nice predictive theory can work, is that it can tell you where to look to find something new. So this is typically how science sort of works. Now we're going to keep this in mind and try to think about that as we go through some of these other stories. So we're going to start off, we're going to make up some atoms. And first there was this guy Dalton, right? And he said, there's atoms, there's little billiard balls, and there's a bunch of different kinds of them. There's red ones, green ones, oxygen ones, chlorine ones, hydrogen ones, and they were just little billiard balls, and you could combine them in different ways. And he made a table of all these different elements, which is really useful. You could talk about some chemistry stuff, but wasn't much detail in there. And then this guy Thomson comes along. There's this little negative electrical thing that can come out of atoms, and that's our first particle. We're going to see our particles show up over here. There's our electron, and now our model looks a little bit different. This is the plum pudding model. It says it's like there's a big bunch of sponge cake, which is plus, and little raisins that are the little electrons that are in there. And that's we keep doing that. Now we're going to take a little bit of a detour. Maxwell, he talks about, there's light waves, and they look at black body radiation. This is, when you make something hot, it glows, and they say, well, how much light should I be getting off? And that was a bit of a problem. Planck comes along, around about 1900 and says, I can explain the stuff that's here by assuming that the light that comes off in chunks. And they're called quanta, little chunks of light. And then there's this other thing, this photoelectric effect. You guys have heard about the photoelectric effect? If you shine light on a metal, you can get these electrons to shoot out. And then Einstein said, I can figure that out and say, now I've got, let's go, there. Now I've got my photon over here. So I've got my photons, they've got energy and everything. And then I said, okay, well, I've got these two things. Rutherford comes along, he takes these alpha particles, shoots them at stuff, and realizes that positive stuff, it's not the whole pudding, it's just in the middle. So we have a new picture of an atom that looks sort of like that. People have been seeing this picture for a long time, but we're going to go a little bit beyond that. Then Bohr comes along and says, look at all these atomic spectra, those little lines that when you throw something in the flame, it glows, different colors, red, yellow, purple, green, whatever. Look at those and say, I can explain those if those electrons were just circling around at different distances away from that big positive charge, and they jump between those things. Didn't tell us why they jumped and why they had to be those particular sizes, but there's that. Then this fellow here, Louis de Broglie, did a very strange thing. He said, well, if photons have energy, maybe, so that's things that are waves have energy, like particles can have. Maybe particles can have wavelengths like waves have, and so we get this idea that everything has both a wave nature and a particle nature. He combines that with Heisenberg uncertainty principle, and we get Mr. Schrödinger and his famous wave equation. So this is an equation that says, these things, these electrons, they really sort of behave like waves, and if I take this idea that there's momentum and energy seriously, I can do stuff, and then we get this quantum mechanical model where we have we've got our s orbitals and our p orbitals, and you guys have seen some of that in your chemistry. So we're getting pretty much along. This is a chemistry lesson in 10 minutes or so. But we're not done yet, because this equation, Schrödinger's equation, didn't take into account a very interesting experimental result over here. This fellow Stirling Gerlach, they took some of these electrons and they put them in a magnetic field that was stronger at one side than the other. If you do that, if you have something that has a magnetic moment, it's going to bend in that field. And they shot that, and they were trying to figure out what's this thing. And they found out that there was actually two dots. There was one dot that was up, one dot that was down, and there was nothing else in between. And said, oh, it looks like the magnetic moment of these electrons can only be up or down. And that was called spin 1/2. And then Pauli takes that and says, hey, if I put all that together with the Schrödinger wave equation, I can make all these orbitals, and I can make the entire periodic table, which is, that's a really big step. I can explain the whole periodic table and most of chemistry. So that's good. Are we done yet? End of story? You don't think so? Okay, what's missing from this? What's the other thing that Mr. Einstein's really famous for? Relativity, yeah, because this thing here was not a relativistic wave equation. It was only good at low energies. And so Paul Dirac made this relativistic wave equation. And when he did that, he found that he sort of split things up, and his equation gave him two solutions. It said, hey, I got a solution for my electron, but there's this other solution with the opposite charge. What's that doing there? Well, I said, well, maybe it's just a fluke of the math, or maybe there's something real. So what do? You go look for it. And a few years later, Anderson finds that positrons are real. They are real objects. And so we've now got our first bit of antimatter showing up. Now, we think, okay, well, this is doing pretty good, but we still got a little problem. There's these atomic spectra. If you look at the really fine structure on there, some of these orbits that are supposed to have one level actually have a couple little things, and it's called the fine structure constant on this thing. And if you take this fine structure constant and try to explain all those things, then Richard Feynman, just up the road at Caltech, makes this thing called quantum electrodynamics, which is a relativistic wave equation that explains all of these fine structure things. It's what's called a renormalized field theory, and we're going to talk a little bit about this, because this is we're getting beyond where a lot of people are sort of comfortable at. So let's have a look at that. Here's sort of a picture of things. This grid here is sort of an electron field, and here's the wavy part of the electron, and say, well, if I have this much electron wave, I have really a particle there. And then here's another field. And I'm just going to play a little bit from, this is it's a PBS.
Space itself is comprised of fundamental quantum fields, one for each elementary particle. Those fields oscillate, vibrate with different energies, and those oscillations are the electrons, quarks, neutrinos, photons, gluons, etc. that comprise the stuff of our universe. Now, these fields are quantum fields, which means their oscillations can't just have any old energy. They can only be excited in quantized chunks, integer multiples of some baseline energy, in each quantum state. So each combination of particle properties, there's a ladder of energy levels, a bit like electron orbitals in an atom. Each new rung of the ladder represents the existence of one additional particle in that quantum state. In fact, the math of quantum...
Leave him here. This is Matt. He's from Spacetime. It's a very fun PBS YouTube channel and everything. But this thing here, what we think of as those oscillations actually are the particles in those fields, and you can have lots of different kinds of fields. And one of the things that's going to happen is, well, how does this field here talk to that field there? Well, they have to talk to each other somehow. And so that's through something that's called coupled oscillators. These are things that are oscillating, and you have to couple them together. So I have another little one.
This is about coupled pendulums. This is a bit of string, and from the bit of string, I've dangled two pendulums going through a cream egg with a little button on the bottom to make sure that it doesn't slip off. Now then, if I bang one of these pendulum forwards like this, it will eventually stop again. Look, I bang it like that, and at a later time it's stationary. And at a later time it is stationary. It's magic. And I remember a magician showing this on a television show where he put a handkerchief in.
But what's going on is there's some coupling between these two fields. And so if I have an electron that's oscillating, that makes a oscillation in this field. If the oscillation is big enough, I can make a photon. That photon chases away, and I've made another particle. By wiggling this field, I can make particles over there. That's how pretty much all of the interactions and the forces that we understand really, really work. So, and the other thing that happens is, if I take a photon and I toss it to somebody else, they're going to feel a force. And I don't know, but does anyone have did anyone bring a skateboard or anything like that? No one? Yeah, there's a skateboard over there. You want to bring that down, because I just, it's, and I'm going to throw this thing at you. You're going to stand on the skateboard and promise me that you're skilled at this, right? So, but if you just stay there on the skateboard, if I toss this thing to you, you move back a little bit, and then toss it to me. Again, you feel a little bit of push, and that's how all of the pushes and pulls. Thank you very much. Thank you very much. That's how all of the pushes and pulls in our physical world seem to actually happen. This is a diagram. This thing here is what Richard Feynman made, and it's a diagram. This shows an electron, and he's moving along here. He shoots out a photon. When he shoots out the photon, he recoils away. That photon goes over here. This other electron basically catches the photon, and then he recoils away on the other side. And the funny thing is that this photon here is not like a real photon. It's a virtual photon, in that it the energy of this photon comes out of the vacuum field, and it goes back into the vacuum field. So what happens is these things are very sort of strange, because not only can I throw a photon from here to there, but I could throw a photon and it could break into a couple electrons and then come back together and do that. And the really strange thing about a lot of this stuff is that every different mechanism to get from here to there, they all happen all at the same time. And what we have to do is add up all those different effects to figure out how much force the electrons do feel on each other. And that gets pretty complicated to do. And if they take these atomic spectra and the fine structure constant, and we try to measure something very, very accurately, what they do is they get an electron in a magnetic field, and it's going to process around. They measure that processing speed. And if I take, oops, I'll go back there. Mr. Dirac's thing, he said that thing should have been exactly 2. And we measure it, and it's a little bit more than 2. And here's what we measured that thing a little bit more than 2 to be, 1.00159652181, blah, blah, blah. If you add up enough of these different things, the prediction from this theory says it's 15965218073. How many significant digits is that? How many of these things do they say? 1, 2, 3, 4, 5. At least 10 digits. That's like 1 part in 10 billion. This is one of the most accurate measurements that we've ever made, and that is one of the most accurate predictions that has ever been made. This theory, strange though it is with all these virtual particles, is very, very predictive of what happens in the real world. So this is one of these things where you say, as strange as this thing feels, if it gets things that right, there must be something in it. So we've done all this. Feynman, he did this work in like 1948. He finally got a Nobel Prize in 1965. But this was a very big step. This is the basis of all the other theories that we have. That's why I wanted to take a little bit of time to make this go along. Now we've made our atoms out of all this stuff, so let's go on and think about the strong force. I call this a colorful story, and you'll find out why. First of all, what do we know? Well, we've got neutrons, and so our basic picture that we have for so much is the electrons go around, and the neutrons, the protons, they stay in the middle, right? And these guys here, they have to stick together somehow. And that nucleus is like really, really small. How big is an atom? Anyone know how big an atom is? 10 to the minus how many meters? Yeah, 10 to the minus 9, 10 to the minus 10. You measure things in femtometer or in nanometers, and so on like that. The nucleus itself, about 10,000 times smaller. So this thing here is about 10 to the minus 15 big. And so these things here, it's a very short range force. And if you remember that Heisenberg uncertainty principle, it was saying, well, okay, I could only have, if I know my position and my momentum, I can only know so much. If I have a particle that travels from here to there, and it's one of these virtual particles, if it can only go a very short distance, I could make a very big, massive particle that goes a short distance, and it's going to be okay with the Heisenberg uncertainty thing. So he's looking for a massive particle that's holding these two things together. The photon is what holds atoms together. That's the electric force. This is a different force. And he thinks it's going to have a massive particle. So he goes and says, well, fine, okay, I had this sort of theory. It's sort of a rough theory. It's sort of like your Kepler theory. It's got a feel to it, but it's not got a whole lot of numbers and stuff. This is still back in the early part of the century, 1930s or so. They didn't have any of those big accelerators like they have at CERN and things like that. So what did they have for an accelerator? Well, they had the sun. The sun will shoot out these protons, and they got a hefty 10 to the 15 eV. Your atoms in your chemistry, they have a few eV. This is 10 to the 15. And so this thing is coming shooting out of the sun, hits the top of the atmosphere about 35 kilometers, and it hits something, and it just makes a spray of stuff. And so it makes some other neutrons and protons, some of these guys here that decay make electrons. And when you get down to the bottom, this guy here is made about 1 million different things. And these are the kinds of things that they're looking for. Well, we know about electrons, we know about photons, neutrons, protons. Oh, look at this guy. Here's 1.7%. And said, maybe that's it. So they went looking for this thing, and it's called the Muon. And they said, hey, okay, let's take its properties. The only problem is it didn't interact with the neutrons and protons. It was like a big heavy electron. Who ordered that? That wasn't what they were looking for. So they just said, okay, well, we've got these other things, but there's some other things in here. There's these little things called pions, and they started looking at those and said, yes, I actually can make those pions do interact with neutrons and protons, maybe, and they have, a middling sort of mass, maybe they're the right kind of thing. But we have to sort of figure out how to do this. Well, something happened between like 1939 and 1945. What was that? Yeah, things got messed up for a little while, but after that was all over and the war was over, this fellow Ernest Lawrence, he found a way to make these cyclotrons, and if you go up to Berkeley, to the Lawrence Berkeley lab, oops, the Lawrence Berkeley lab, no, come on, back. There we are, get the pointer. Yeah, the Lawrence Berkeley labs, you will see that they had these accelerators. They were able to make some more of these things. So first up at Berkeley, they made pions and they made antiprotons, our second piece of antimatter. They had enough energy they could start making those things. And then they keep, making these things a bit bigger, and they start getting a whole bunch of these other things, rho particles, K particles, phi particles. Boy, we're just getting a whole bunch of stuff showing up here. Over at Rochester, New York, they have a couple of these things. They get these things that are called V particles, kappas and lambdas, and they're put them through these things. They're called bubble chambers. What they are is it's like a big thing that's just ready to form a cloud. If you send a little charged particle through that ionizes some of the atoms as it goes through. Those ionization centers become nucleation centers, and you get a little streak of cloud wherever a charged particle goes by. And they found that some of these things, look, came along here, and then obviously it wasn't charged, but then it decayed into a couple other charged particles, and said, oh, this is, got a whole pile of stuff going on. Eventually, this stuff, they just called it the particle zoo. There's, 10, 15, 20, 35, 60 different particles. And they don't know how to make sense of this stuff. It's like having a periodic table, and there doesn't seem to be any really good structure to it. And then the people up at Stanford, this is the Stanford Linear Accelerator, they were actually doing a different kind of experiment. They were taking, and they were accelerating electrons. Electrons are nice, simple particles. They're a fundamental particle. They're like a little dot. And if you shoot them in, and just like Rutherford, they sort of scattered things off of the nucleus. And if you get them to high enough energy, they started going through the nucleus, and so they could tell that this was no longer scattering off of a point, it was scattering off of a sphere of charge. And so this was our first evidence that these guys here, that proton, was not a point particle. It was something that had a real size. It's a little bit less than a Fermi. 10 to the minus 15 is about 0.8 something, times 10 to the minus 15 meters. And they figured that and said, well, okay, if a proton is not a point particle, maybe it's a composite particle made of other things. And this fellow, Murray Gell-Mann, came along and he made this Quark model of say, well, okay, I can take these things and say, oh, okay, I can say a proton has got, two of these plus 2/3 things and one of these minus 1/3 things. They call these up quarks and down quarks. And I can explain a proton. I can explain a neutron by having 2 to the minus 1/3 and a plus 2/3. That all cancels out, so I get a zero charge on that guy. And then our pion guy, well, he looks like a plus 2/3 and then an anti of the other one. That gave me a plus 1/3. That gave me a plus 1 on that. So I could explain several of these guys just with these two things, an up and a down. And from this, he said, okay, well, all these other guys here, if I have one more guy, and he's sort of a strange guy that makes all of these particles, and he's just going to call it the strange one, but he said, okay, I've got three up, down, and strange, and he predicted that, well, if I can combine them in these ways, there's a combination that I can make that we've not seen yet. And this was called an omega minus. He publishes his paper. About 3 weeks later, they find it. So, you know, all these things are happening, and said, hey, well, and they didn't find stuff that the model didn't predict. That's also an important stuff. There's no things that it's not really predicting at this point, and said, okay, fine, but I have these guys here, but I still got 2 plus charges and right next to each other, still got 2 minus charges right next to each other. What keeps those things together? Well, you know, physicists being what we are, well, if you want to stick two things together, what do you use? Glue, yeah. So we call them gluons. And this fellow Greenberg, he said, okay, I need stuff to hold these things together. So now our model looks sort of like this. I've got my quarks, and these little wiggly spring-like things are those gluons that are holding it together. And I brought along a proton here. Here's your basic proton, and you know, if I toss it up in the air, it stays together, and it stretches around and everything like that. I have a proton. Oh, and I've got one of my pions here. Yeah, I have a regular one. I got an antiparticle on this side, and you know, they stick together. So okay, fine. We've explained how things stick together, and we needed this other thing, and we have this other thing, just like the photon. This carries force between two things, so it's pretty much in the same category as a photon. It's a force carrier. Do you think we're done yet? I got space left on this slide, so okay. But this guy here, Bill Gross and Marie Gelman and a bunch of other people, they take that theory that Feynman put together, quantum electrodynamics, and they make it they call it quantum chromodynamics. They call it chromo because there's colored gluons. I figured that sounded a whole lot better, because if it was quantum electrodynamics, it should have been quantum gluodynamics, but that didn't sound so good. So it became quantum chromodynamics. So, but this was exactly the same structure as Feynman had for his electrical charges. This thing, I have a force carrier. I've got particles that have a charge on them that happens to be something that this gluon, you know, sees as a charge. And just like before, they looked at some of these things, then they looked at how many of these, and they start doing calculations and say, oh, okay, what should be the lifetimes of these things? And then this fellow Sheldon Glashow, he makes a really precise calculation and says, you know, this stuff isn't matching precisely with what we see, but if I added something else in, then yeah, it would match. This is sort of like how we were finding Neptune. They said, oh, you know, in order to make my stuff match what the experiment, I need an extra piece. And that extra piece was called a charmed quark. These two guys here, Ting out here in Stanford, and no, Ting was back in New Haven, or upstate New York, and then Richards was out here at Stanford. And they both were finding it. One called it the J, the other called it the side, but it's a particle that's made of this new quark, and he's called a charmed quark. There he is right up there. Why would he be called a charmed quark? Well, again, it's one of these funny stories that this particle, because it couldn't decay in the way other things could, lived a very long time. So they said he lived a charmed life. So this is what you need to live a charmed life, is you need a charmed quark. And then, of course, well, they said, well, let's keep bashing stuff together. And eventually, another one come up. And this was Leon Lederman up at Fermilab. And he knew he was looking for another stuff. He already had it named. It was going to be the upsilon particle, because that had Leon in its name. So it was the upsilon particle by Leon Lederman. Well, they did a bunch of experiments and they saw a little peak coming up, and everyone got really excited. Oh, we found it. And they took some more data, and the peak slowly disappeared. And so they called that one the Oops Leon particle. But they eventually did find a particle that was really there. They could reproduce it, and that was called, and they're starting to run out of silly names, so they just called the bottom quark. And it's just like the down and the strange. It's just heavier than the other things. Remember, we had that electron and that funny heavy electron? Well, these are like this. I've got my lightest quark at -1/3. I have a heavier -1/3 and an even heavier -1/3. So what do you think's missing? Yeah, okay. And a little bit later, up at Fermilab, they discovered the top quark. And there he is up there. And we've sort of completed this chunk of our table. They got a Nobel Prize. He published his 1964. He gets the Nobel Prize 5 years later. That's actually pretty darn quick. And it was, basically it changed the way people thought about all of this mess of the particle zoo. We got the zoo down to six people of only two types, the up type and the down type, and their heavier cousins. And now, I know I promised you no equations, but we're going to do a little bit of, just a little bit here. Why do they have to have fractional charges? Well, why can't we just use 1 and 2 or something else? Well, let's look at this a little bit. There's some rules for building up particles out of these things. Every composite particle has to have an inner charge. It could be a minus, or it could be a 0, or it could be a 1, but it can't be a fraction. So when I add things up, I have to get whole numbers. Middleweight particles, like this guy over here, they've got two quarks, a quark and an antiquark. And the heavyweight particles, this guy over here, protons, neutrons, and so on, they've got 3 quarks. So if we just say, okay, well, they can't all be the same. So we're going to call them A and B. And the antiparticles have minus A and anti-B. And if I put a couple equations together and say, okay, well, A minus B has to be 1 to get this guy. 2 of these plus 1 of those gets me a 0. Like, that's my neutron. 1 of these and 2 of the other ones gets me 1. If I solve the equations, what do I get? I get minus 1/3 and plus 2/3. So, it's just, this is algebra, and that's why we have to have those fractional charges. And we can explain all those other particles with just one more minus 1/3 quark called strange. So all of that zoo that we are making, we can come up with that. Now, remember I said that the gluons were colored gluons? Why do we have to have so many values for that? Well, each quark is got a spin 1/2. It's like an electron. And when we're building atoms, can we put 2 electrons in exactly the same place? This is the Pauli exclusion principle. We got to, if they're in the same place, they got to have different spins. But let's look at a particular particle. Here's one, it's a DDD particle. It's got 3 down quarks in it. It happens to be called an omega minus. And if all my spins are up, and it's got a spin of 3 halves, so all my spins are pointed in the same direction. We can measure that. They have to differ in some property, otherwise they can't all be there in the same place. And we call this property color. And we call it, and we use the values, red, green, and blue. They're not red, green, and blue. We know that. It's just a fiction that says, okay, there's 3 different things, but we use the colors because they sort of do this. My guy here, if I've got red, green, and blue, I think if I add 3 of them together, what color do I get? Wait, so outside the quark, outside the proton, it looks like it's got no color at all. So these guys here, they hold the colored things together very, very strongly. But when I make my particles, they're uncolored. If I look at this other one here, this is a quark and an anti-quark. So I have like a green and an anti-green. Put those together, a colorless particle. So this strong force, when you put things together, you're going to make colorless things. Otherwise, the strong force just wouldn't have let it get away from you. And we're going to see these things. So, okay, these force guys here, these little springy things, they're called gluons. And interesting enough, to make this whole system work, they have to have 2 colors at the same time. What happens is I have one of my quarks coming up, he's a green one, and he shoots at a gluon. That gluon takes a green and anti-blue. This guy here becomes blue. That gluon goes over this guy. The anti-blue cancels the blue here, the green takes over, and like that. So these guys here end up switching colors, but to make that work, we have to have bicolored gluons. So the gluons themselves are colored. This makes it different than electricity because the photons don't have any charge. And so this is part of what makes the strong force like really strong. The things that carry the force themselves feel the force. And now, after all of this talking, we can actually finally get back to 1935, Mr. Yukawa and his particle that held the neutrons and protons together. So here's my neutron, and here's a proton, and they're exchanging this pi particle. This is this meson. And what happens is when this guy exchanges, this guy turns from a neutron into a proton. He goes across, this proton changes into a neutron. That seems sort of strange, but if you look inside, we can actually see what's happening. Inside, what we have is a neutron coming up here, up, down, down, and they're going along, and one of these guys shoots off this d particle, and a gluon goes up this way. Meanwhile, this guy here, he basically collides with an anti-up to make a gluon that goes up here, and like this. And so what happens, we really do see that this particle that travels between them is a d and an anti-u. That's a pi minus. So this is what's really happening inside Mr. Yukawa's force, and that's holding the neutrons and protons together inside the nucleus. So this is why our nuclei stay together. It's this property here where we're actually exchanging a heavy particle, but we do it by sending a quark from this side to that side and one from this side to the other side to make that happen. So that's what's, you knew that you're going to learn more about quarks and what they were doing, but this is what's really going on. Quarks are the quarks. You may have noticed a couple different things. I'm not sure if you looked at it, the mass of the up quark is like 2.5 MeV. The down quark, a little bit heavier at 4.8. Our electron is about half an MeV. And the gluon itself is 0. It's just like the photon, it's got no mass. And then I go measure the mass of my proton, and it's 938. Anyone see a problem with this? How can this thing here weigh more than twice this 9.6 MeV? What's going on, folks? Anybody have a clue? Well, that proton is really, really small, right? If I try to squeeze things into a really, really small space, what happens? Heisenberg uncertainty principle says they got to go really fast. If they're going really fast, what kind of energy do they have? They have kinetic energy. So the quarks and the gluons themselves have kinetic energy. It adds up as additional mass. So, we've all seen E equals mc squared. Well, actually, really, this is what it is. My total energy is mc squared, and I add on my momentum there. I can see this is my hypotenuse. This is one edge. That's the other edge. So here's my energy here. There's my mc squared. There's my mass. And then here's my here. And my kinetic energy is this little bit up here. If I do that, we basically see our picture of the proton really should look like this. This red, green, blue smear zipping around very, 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 very fast, because that kinetic energy gets us all the way from 9.6 to 900. So believe it or not, you are about 99% energy. So but we see it just as mass, but for us it's mass. It shows up as the mass of the proton. That thing moves around. We have to push it like it has that much mass. But that's just because of all the energy of those little quarks whizzing around. Another question. Why can't we get those quarks free? What happens if we would try to get a free quark? I mean, why can't I get a little green quark just zipping along? Well, let's have a little look and see what happened if we try to do that. They're always combined in particles. You can't get them out. Well, there's something that's called quark confinement. This is sort of how it works. If I have, this is a little meson, it's a charm, anti-charm, and I take this thing, okay, let's go backwards. Take this thing and I whack it really hard with an electron. I go up to my Stanford Linear Accelerator and I whack it really hard with an electron. So I'm going to take that top one and I'm going to whack it. Well, it starts to stretch that guy here, right? He starts to stretch one of these guys. And if I'm stretching an elastic band, I'm putting energy into it, right? Well, if I keep stretching long enough, I have enough energy so the thing snaps. And what it snaps, it does is it changes that energy into a particle-antiparticle pair. And those things then fly off, and so I now have another colorless particle on this side and a colorless particle on that side. I've just taken this thing and I've actually made a new particle, and so I took my electron, whacked it on here, and out come two. But they're both colorless, they're both confined. If I try to stretch one of those gluons too far, that energy that goes into the stretch snaps back and turns into particles. So that energy in the gluon field that is oscillating, it couples over to the quark field and makes it make a particle-antiparticle pair. We're going to go and build a few atoms as a prelude to the last part of this thing. So we've done our electromagnetic force, we've done our quarks and the strong force. Let's just try building a few nuclei. And I'm going to turn on some of this stuff, unstable. And so I'm going to just sort of drop a proton in there. And this thing, and okay, fine, we got a nice hydrogen atom. Let's just drop another proton in there. Oops, that thing's not stable. That won't stick together. I can't stick two protons together. So let's put some more glue in there. We got that. Fine, okay, well, let's add more glue. Hey, we're great still. Oh, I still need another electron to balance up. There we are. I got a neutral helium atom. Let's throw this thing. Oh, if I add too many neutrons, I also get unstable. So there's something, I have to have about the right number of each thing. So let's, doing this, I can add that. I can add some here. Eventually, I get stable. So there's something about how all of these things work that we have to figure out a little bit of what's going on. And so I'm going to go with a little bit of my nuclear engineer hat on and say, well, okay, if I look at the mass number, how many of those things I put in there, and I look at how much energy is holding that nucleus together, it actually, at some point, roundabout iron, I get as much energy holding it together. That's my tightest bound nucleus. It then goes down. If I get uranium-235, it's actually less than this over here. So when I have a nuclear reactor, what I do is I take this thing, I break it into two parts about this size. Those parts each have more energy per nucleon than the uranium did, so I get that difference out as energy available out of my nuclear reactor. The sun, on the other hand, it's putting stuff together. He goes basically from 1 to 2, and this is how much energy he gets by building a helium nucleus out of protons. And so he gets a whole lot more energy per nucleon out of the fusion that's in the sun. But if we look back and think about all those different things that we made, the black stuff in here, those are our stable nuclei. If I put too many neutrons, I'm up here, and those are unstable. If I put too many protons, I'm down here, and those were unstable. And if we look on here, there's these interesting numbers on here. You remember when we were doing the periodic table and we had some elements that were particularly stable? Those are our inert gases or noble gases. Those are, those like had complete shells of stuff. Same thing happens with these guys here. These are stable filled shell numbers. And they're the same for neutrons and protons. And sort of like with that, if you're away from that, you can get very reactive things. And if you look here, there's some gaps in here which are particularly unstable. You don't have any stable element with, whatever that is, 21 protons. And so, and then if you're having too many neutrons, what does it do? It pops out a beta, changes a neutron into a proton, and I get closer that way. If I had too many protons, I pop out a beta plus, I change a proton into a neutron, and it moves that way. And then again, at the very end, if I'm way up there, I can shoot out a whole alpha particle, and I move down that way. So obviously, the stuff that we've built in these nucleuses is not stable. So what's going on there? Well, that's our last force. Our last force is this weak force, and I call them decadent particles because they're decaying away. But they start off with our good old friend Madame Curie, and they have radiation. This is our first radiation. And we already know about electrons. Then they look at these, Pauli looks at beta decay. This is where I'm changing a neutron into a proton, and it spits out this other particle here. I know that there's at least one or two physics professors in here. If I have something that's sitting here and that explodes, I'll have two things coming out. If there's a total energy, Those two things have fixed energies. I can't really monkey one around from the other, right? They will have fixed energies. Yet, if I look at the energy of the electrons coming out of one of those things, I don't get just one energy. I get this whole spectrum energy. I get up to a maximum, and then it drops off. I get more of these sort of things. And so they're saying, well, just with simple mechanics, there's got to be some third guy around. And so they called this thing the neutrino. And Pauly says, what have I done? I've just decided that there's a particle that has no charge, it's got no mass, it's got no color, I can't see it. How does it do anything? But it's got to be there because that's the only way I can explain the fact that that spectrum doesn't have just one peak at the at the energy that the electron would have. So there's something there. And then Enrico Fermi, he makes a model. It's very much like sort of a Kepler model. There's not a lot of understanding in it. They're saying, okay, if I fit the curves and I can do some things, I can make some transition probabilities and things and like that. And then they notice, well, if I have free neutrons, if I just have a lot of people don't know this. If I just have a neutron and it's just tootling along on its own, it's not stable. A free neutron is not stable. It lasts about 6 minutes, and so neutrons themselves will decay. So a neutron itself is not the lowest state that stuff could be in. It decays into a proton, so apparently a proton must be a lower state than a neutron. Remember our friend the muon? Well, he's... Hello. Stopped responding and has recovered. Well, very nice, thank you very much. So they finally have these accelerators and they can make these muon beams. So we have our muon there, and our good friend Leon Lederman, he decides, he looks at this and says, oh, I take those muons, they go along, and they decay. They're not the lowest form either. Remember, so this heavy muon can decay into his lighter cousin. And what does he shoot out? He shoots out a muon-type neutrino for doing that. And then they say, okay, again, we have the same problem that Yukawa had. I need to have somebody that's causing these things to happen. This is a very weak force. Compared to the strong force, it's like very, very weak. It's going to be a very short-range force, so we're going to have, again, a massive particle. And what we look at it and say, well, okay, I'm going to say, okay, Have got an extra down quark that I have in my neutron, and he wants to change it into an up quark. And what he's going to do is he has to conserve charge, so he has to spit out a charged particle. And that charged particle, that particle carrier moves along here, and then he makes an electron and one of these neutrino guys and says, okay, I can do that, but now I have charged carriers. My photon had no charge. My gluon had no charge. These guys here, they got charge and mass. They get more difficult at this even more. So we got charge and mass to try to figure out what's going on. Here's our neutron decaying into a proton, shooting out this W, and like that. If anyone see my badge, I have that little symbol on my badge that I wear around the tutoring center. That's where that comes from. The sun, remember, it takes hydrogen and it makes helium. Well, in order to do that, it's got to take a couple of those protons and change them into neutrons. When it does that, it generates neutrinos. Fusion in the sun, if you hold up your thumb, every second there's about 10 to the 11th, or that's what, 100 billion neutrinos going through your thumb. And you don't notice them. That's why it's a really, really weak force. You could have 10 10 to the 100 billion neutrons go every second, and you don't even notice it. So let's have a look and say, well, what kind of things can happen? Well, here's my quarks. Here's my plus 2/3, my U, my charmed, or my top, my down, my strange, and my bottom. And then I can go from one side to the other by emitting a W plus, and from this side to that side, going that way. And then from here, I could go to any one of these things, but the darker the line is, the more likely that thing is. Remember back when we were talking about the eggs and the coupling between two things? All these different sort of transition probabilities are some of the parameters that go into the standard model that says what makes these transitions more or less likely. And that's part of our description of the world. But everything rolls downhill. So you can see that my extra D rolls downhill to my U, and that's why my proton is more stable than my free neutron. But this doesn't just work with quarks. Here's my heavy electron, my muon. He spits out a muon neutrino and one of these guys, and he decays and spits out an electron and another electron neutrino. So I can use that. I can use the same force to change electrons into, down the scale this way. I can also use it to get rid of particles entirely. Let's go back. Here's my pion. That's the guy that we exchange when we're holding neutrons and protons together. Well, again, he's unstable. He flies along a little bit. After a while, my down and my anti-up, if I look at this thing, I can say, here's my down going this way, my anti-up going that way. That's a vertex. I can throw off a W particle to one of my weak charge carriers, and he flies off this way, and then he decays again into electron and neutron. That's how this guy here just decays. He goes away and becomes something else. And so this weak force, he does a whole lot of work. He can make anything run downhill. Now, let's see. Yet, we've got one more twist on this whole thing. Again, darned experimentalists, they go and they measure stuff. And sometimes they don't get what you would expect them to see. Wu, Chinese lady physicist, 1958 or 57? 57, yeah. Tries to measure she's got a cobalt 60 atom in a magnetic field and wants to see where the electrons come out when this thing is allowed to decay. And she puts in the magnetic field so that, and then she's expected I could get just as many coming down as going up. Well, when you look at this and everything and say, well, okay, if all these are going down, then the neutrons must be, or the neutrinos must be going up. And that means that every neutrino that went up is what's called a left-handed neutrino. It's, it's got a spin, but its spin is, I think, opposite to the direction of its motion. But the rest of the world's supposed to be symmetric. It doesn't really matter whether I go left or right or whatever it is. Something very strange is happening with these neutrinos and this weak force that it's no longer symmetric. So this fellow Higgs, he put together a idea, and it's actually very ingenious, and we've got some extra slides if we have time to talk about that. But he says, oh, if I have a mechanism that will break my symmetry, it actually gives mass to these things, and it joins together both my electrical force and my weak force to make it one thing called the electroweak force. And it sort of, you can think about it like this. If I have states of matter, I mean, I've got gas, liquid, solid, and I've worked with I worked in plasma physics, so I always include plasma. But all the gas and liquid, they're the same in whatever direction that I work, right? But when I get to a solid, it makes crystals. So now, when I get it cool enough, I actually get special directions. Sort of like being only left-handed or only right-handed. And that's actually the mechanism that they used to explain this. This Higgs thing is like that. And the temperature of the universe is slow enough now that it's basically frozen into one of its particular states. So things only go for things in the left-handed way. And these three, Weinberg, Salam, and Glasgow, they made this electroweak theory. And when they did that, they said, okay, oh, I have something showing up in my theory. I haven't seen any of these. It's another force carrier. It's a neutral force carrier for the weak force. That's nice. Maybe go look for it. Let's see if it's there. Otherwise, my theory's crap, right? So they go, and over at CERN, they detect what is called weak neutral currents. You can't see the carrier itself, but you can see the result of interactions that carrier is made happen that can't be explained any other way. Pretty tricky experiment to do, but that's okay. Well, it looks like that thing's really there. So now we've got not only my W boson, but I have a Z boson. Those both are part of the electroweak set. And now, oh, of course, people at the other labs, they keep working along. I got one more of these heavy electrons. It's called a tau. And if I got a tau, what else do I got? I have to have a tau neutrino. So they look and they go and they find those things too. So, okay, well, this is sort of interesting. I got 3 kinds of electrons. I had 3 kinds of down quarks and 3 kinds up quarks. Well, okay, but this is looking interesting. And then finally, they upgraded the big accelerator at CERN, and they actually were able to produce these charge carriers by themselves. It's like getting not a virtual photon, but a real photon to come out of your experiment. So they actually were able to see these things. They measured their masses, they measured their lifetimes, they agreed really very well with the theory. And then finally, 2012 or 13, I mean, this is a long time after this thing was done, we finally see the Higgs. And I mean, some people have seen them at the CERN thing singing, you know, Higgs, glorious Higgs, and so on like that. But this was a really big thing. It's been predicted since 1967, since Peter Higgs did this. And that happened in 2012. They actually found it. Peter Higgs did his paper in 1964. He got his Nobel Prize in 2013. So it was a long slog to get to this bit. But now we have everybody in the family. So let's, oh, and then these guys here, for this theory, they published that in 1967. That's 50 years ago this year. They got their prize about 12 years later. So we've now put together all the bits and pieces. So here is our entire family of particles. We've got quarks, and we have these things that are called leptons. Leptons means light things. And then in this column here, these are all of our force carriers. The photon carries electric force. The gluon is anything with color. And the Z and the W boson, they take anything and will move it down, you know, back and forth across here. So let's sort of have a look. So we had a total of, if we count the different colors and the generations and things, you know, actually a total of 61 distinct kinds of things. But they're actually, you know, put together in pretty good families. So Here's our photon. He takes everything with charge. Well, all those guys have charge, all these guys have charge, so they all interact with the photon. The gluon, he interacts with all these guys and himself, because he's also colored. Here's my two force carriers for my weak force. They take care of everything that's matter. Everything that has, we call it flavor. These are different flavors of matter. And so they can decay quarks into quarks, electrons into electrons, and the neutrinos, there's a more interesting story that's actually beyond the standard model, so that's another talk. Oops, there we are. And what else do we have? Oh, there's Higgs. Higgs is the thing that interacts with things that have mass. We say it, quote, gives them mass, but and so Higgs itself has mass. All of these particles have mass. These two force carriers don't have mass. The neutrinos effectively don't have mass, but those guys do. So this Higgs makes all of these guys here feel the force of mass. They're the only thing that allows something to stand still. Mass allows something to stand still. If it had no mass, it has to move at the speed of light. So those guys there always move at the speed of light. These guys here, they pretty much move at the speed of light too. But all these guys here, they can actually slow down and stop. We can stop electrons. So, okay, I've been talking for a good while now. Let's have a little bit of a review of what we have. We've got different kinds of particles. Here we've got things that have an integer spin. These are all my force particles. Photons, W plus and minus, gluons, Higgs particles. Those are all of my force particles. They've got integral spin. And I can make integral spins by connecting a composite particle. So this guy here had a spin up and a spin down. So I could make a 0 spin, or I could do a spin up and a spin up to make a 1 spin. These guys here, that's my pion. That's sort of like a force carrier as well. So all of my things that have integral spin have that. Then there's my matter particles. And these things here, all the quarks can only come in grouped chunks. I've got hadrons and mesons, baryons. So all that stuff is there. So let's sort of think back a little bit about what we talked about. What did we learn about how science works? Well, sort of, we start with evidence, go to a model, go to a theory, we make predictions, and we make tests. Have we seen that happen in this story? I think we've seen that happen quite a few times. What's interesting about the electromagnetic force? Well, it's got our photon and electric charge and our basic theory, which is this quantum electrodynamics that Feynman made. And the real thing that's interesting there is anytime I have a force, let's go back, force, okay. Anytime I have a force, why does that keep doing that? Okay. Anytime I have a force, that's exchanging virtual particles. That's the only way things talk to one another is I have a field that's oscillating. It makes another field oscillate that sends one of these force carriers, and that force carrier makes another field oscillate over here, and something happens. And that's how the interaction gets from this place to that place is I have a matter particle, I have a field, and then I have another matter particle, and that's how the two matter particles talk to each other through the fields by the virtual particles. The strong force, we've got our colors and gluons. And the interesting thing is, everything here has to be composite. I can't make a single quark particle because it's colored, and I can't have particles that have any color on them, so I always have to make them in chunks that way. And they also, because of that, the quarks are confined. I can't get them out. No way I can really do that. And then for our final force, this is what's responsible for particle decay. And the thing that is really strange about that is it's not symmetric. It's one of the first times when nature says, no, that direction is different than this direction. And that's because part of the system that got made has frozen into a particular configuration. And so that's really how that happens. And this is everything on a slide. This is from the people here that is the configuration for particle physics education, and it's actually a great slide. But that's all that I have to say. I'm sure you're... Now, I kept plowing on through that. Do people have questions? Did this make some sense for people? How many forces have I explained? How many forces? 3. The electric, the strong, and the weak. Is there another force in nature? Gravitational, yes. We haven't done that one. Standard model does not take care of gravitation. Gravitation is 40 orders of magnitude too weak for us to worry about. If these things here, gravity, if the electromagnetic force is strength 1, the weak is about 0.8, the strong is about 25, the gravitational force is 10 to the minus 40. So in this realm, gravity is just so weak it doesn't really play. There's all sorts of interest to try to get gravity into the picture. Then they've unified the electromagnetic force. They've unified that into the electroweak force. They would like to have a grand unified theory, which is all these 3 forces. And then they would like to have a theory of everything, which is everything in one thing. And that's when you start talking about string theory.
Oh, yeah. I like that.
Yeah. So basically, Maxwell did this. He unified electricity and magnetism. Higgs and Sheldon Glashow and all those people, they put these 2 things together. They would like to make this thing. Oops. They'd like to make that group there. That's a grand unified theory, a gut. And when they put them all together, it's a theory of everything, and that's a toe. So we can have another talk on guts and toes. And it's not a biology talk. If you go back to the original atom, atom comes from a Greek word meaning not tomos, and that means to cut, means uncuttable. Atom means an uncuttable chunk. That was back Dalton and the billiard balls. They thought those things were atoms, uncuttable. We've been peeling off layers and layers and layers. So far as we can tell, the things like electrons and quarks have no internal structure. They seem to be point-like particles. They got no size to them. And pretty much that's an indication, if you see something that has a finite size, that's pretty much an indication that it's made of other stuff. The next bit, when they try to add in gravity, the energies that they would have to do are things that we could not make in this galaxy. But they are, so it's one of those things that's going to be very hard to do the experiments for. But the mathematics goes all the way, and they can say, oh, okay, if we, and it's quite interesting, the same thing that they did to unify the electroweak, you do the same mathematical trick, and you can get in gravity and avoid the infinities and zeros, because the reason they needed to, with the weak force there, the model that Fermi had was good up to some energy point, and then they started giving absolute nonsense answers. You get probabilities that were bigger than 1 for things happening. And you know your theory is basically it's gotten into a place where it doesn't work. So, and what they did is they basically went in and they tweaked the mathematics to say, okay, we can't have that thing do that, so we're going to tweak this. And there's something where you make poles and zeros in a function, and if you do it the right way, that'll represent a real particle. And they tweaked that sort of thing, and that's how they got that electroweak theory. They did exactly the same thing with tweaking it, because the problem they have again with the gravity stuff is that it gives you absolutely nonsense answers when you try to plug in the models that we have now. So say, well, let's do the same trick again. We're going to go and put in these fudge factors so we don't get the infinities, and the particles that we get look like good particles. And then after they did that, they looked at it and say, well, what do these equations represent? They represent the scattering of strings, of finite-sized things that wobble around. And that's why it's called string theory. But it came exactly out of the same process that we went to get the electroweak stuff to unify. They're doing that with that. Of course, with string theory, they've got, 10 zillion versions of string theory. And since you can't test any of them, it's sort of, I like my one better than yours. And then you start to look for other criteria to say, well, how does this one look elegant enough? And so on. But yeah, eventually you do peel away enough layers, you get enough energy that you start to take things. And that theory basically says that even electrons and maybe quarks and things, they may be a single thing, but they're a kind of vibration of a string. And so an electron is one kind of a vibration of a string, and a quark is a different kind of vibration of a string, and photons is a loop that's doing a dance like this. And so it's all made of one kind of thing, but they're doing in different modes, and that's how we see different particles.